Okay, so in class today we learned how to set up problems. Now today what we are going to do is learn how to solve some of the most common related rates problems. And these are the three most common scenarios you will see. A Pythagorean theorem used where you know possibly two sides of the triangle and the missing side, like the ladder falling down a wall. Volume and area. Now this can be of many different types of shapes. We can do rectangles, we can do pyramids, we can do prisms, we can do all kinds of things. And then also, what if you know a rate of change of an angle? Can you find the rate of change of the sides? So let's look at one of each of these scenarios. So you should be taking notes on the protocol, the graphic organizer I gave you. And so we're going to look at the first problem. Now I am going to slip over to a different page, but first let's just read for understanding. So we have Tweety is resting in a birdhouse 24 feet off the ground, using a 26-foot ladder, so I'm underlining all the facts, which he leaned against the pole, bird holding the house. Sylvester tries to steal the small yellow bird, Tweety's bodyguard. Hector, the dog, starts pulling the base of the ladder away from the pole at a rate of 2 feet per second. Okay, there's one rate of change. How fast is the ladder falling? So this is my unknown. When, so we have a condition, it is 10 feet off the ground. Okay, so using these facts, we're now going to organize it, make sense of the problem. So I'm going to go to my protocol. And the first thing I ask myself, what is the unknown rate of change? So we are wanting to know how fast the ladder is falling. So according to my diagram, I labeled the height y. So I'm wanting to find dy dt. Now it always helps to have a diagram, so I've already started my diagram here. And let's talk about the three aspects of this picture. So we're going to let x represent the base, or like that's the sidewalk, right? And then we're going to let y represent the height. Now this is the height of the birdhouse from the ground. And I'm going to say z is going to be my ladder. That's kind of like the hypotenuse. Now we are told that the ladder is 26 feet long. Now that is a constant. So I'm going to say that is 26. I only put constants down initially when I read it. Now, do I know any rates of change? Do I know the rate of change of x? Yes, they tell me that he's pulling the security dog is pulling the ladder away at 2 feet per second. Now, always write down your units so that you'll remind yourself to answer in units. Now, the change in y over time, that's the change in how quickly the ladder is falling. That is what we don't know. So that's my unknown. Now, what would be the derivative in respect to time of the ladder? Well, since it's a constant, that would be 0. Now, are there any conditions for this problem? In other words, it says when the height is blank, or when the blank is blank. It does. It says, so when the height is 10, how fast is the ladder falling is what we want to know. So knowing that I've got a little triangle going on here, I'm going to be using Pythagorean Theorem. So I first write the equation, x squared plus y squared equals z squared. You always have to identify what equation am I taking the derivative of. Now before I take the derivative, I substitute any constants, because this will make it so much easier when I take the derivative. Whoops, sorry, that did not mean to be a 2. X squared plus y squared, and the ladder is 26 feet long, so it's 26 squared. So now I'm going to take the derivative in respect to time. So it's going to be 2x dx dt plus 2y dy dt. And the derivative of a constant is always 0. Great. So now I've taken the derivative. Now before I solve for my dy dt, I'm going to substitute any values that I know. Well, I do know the rate of change. So I've got 2 times something, and the rate of change of x in respect to t is 2. Okay. And then I also notice when the height is 10, I'm going to find the change in y in respect to t, and that equals 0. So you notice if I were to replace this with x, I actually have two unknowns. I have an x that's unknown, and I have a dy dt that's unknown. Well, since I'm solving for dy dt, I only want one unknown. So knowing that the ladder is 26 feet long and knowing that the height is 10, at that moment, could I find the value of x? Well, of course you could. You could do a little Pythagorean theorem, right? Exactly. So, let me scooch this up a little bit. Oh, that moves my writing. Ooh, that's not good. I want to move the image. Yikes. Okay, so then I would have to use Pythagorean theorem and go 10 squared plus x squared equals 26 squared. Now, I've done the math, and I find out that the value of x is 24. So, x is 24. Now what I'm going to do is solve this problem. So in the blank in your organizer that says solve, I'm going to solve it. Now, unfortunately, I keep trying to move this up. Oh, I can move it up, but the writing just doesn't move. Oh, dear. Okay. I don't know a quick solution. New page and do it. So now I'm going to have 2 times 24 times 2 plus 2 times 10 times dy dt is all equal to 0. So let's solve for dy dt. So we get 96 plus 20 dy dt is equal to 0. And I subtract 96 and divide by 20. And I get the answer is negative 96 over 20. And I could reduce that to negative 24 over 5. Now when you write your answer then, the question was, what is the rate the ladder is falling? So the ladder, now notice it's a negative, which makes sense because the direction is down. So the ladder is falling at negative 24 over 5 feet per second. So there is our first problem. Now let's move on to the second problem. Okay, so now we've got a different type of problem where it's probably going to be a volume or an area problem, because I said that was the second type. So we have a water tank that's the shape of an inverted circular cone. So it's a cone. Base radius is 2 meters when the height is 4 meters. So I'm underlining the facts. If water is being pumped into the tank at 2 meters cubed per minute, it should be per minute. Now the great thing about that is I know that's volume because of the units, meters cubed per minute. Find the rate at which the water level is rising. So this is my unknown. When, oh, here's a condition, the water is 3 meters deep. So the height is 3. Now they do give you the volume for your cone that you will be using, which is always helpful. So I'm going to go ahead and start filling in the protocol. Okay, so you can see I have my diagram already drawn, my inverted cone, and I know that the radius is 2 when the height is 4. So let's start talking about the things that we know and don't know. So our unknown rate of change is the height. I want to find the change in height over time. That's the goal. Okay, now we can see they told us the formula we're going to use is volume equals 1/3 pi r squared times height. So the varying things is we're going to have V is volume. V will represent volume. Now, do we know the change in volume over time? Yes, I believe actually that was given in the problem. That was 2 meters cubed per minute. Okay, now the next variable is, so we've got 2 other variables. We have H and we have R. Okay, now H, the derivative of H in respect to time, that is our unknown. We don't know what that is. And then how about the change in radius over time? Are we given that also? I don't think so. Okay, so we're going to have to work on this a little bit. Because you notice I've got a pi, r squared, and h. And I still haven't used this idea of 2 to 4. Now, we don't know exactly how height, well, we're going to look, oh wait, let me do the condition. Sorry, I almost got ahead of myself. We want to know the change in height over time when the height is 3 meters. Okay. Now, so we're wanting to know the change in height. So you can see we've got some similar triangles going on here. Are you noticing all of the geometry? I've got, this is a 2 to 4 relationship. So no matter what the height is, the radius relationship will always be 2 to 4. So that means we could write a proportion, r is to h, as 2 is to 4. Now, since I am solving for the change in height over time, what I want to do is I want to write radius in terms of height. So I want to solve for radius. So therefore, radius will be 2/4 height, or 1/2 height. So over here with radius, I can say that that will be 1/2 the height. But now we can take the derivative of that. So the derivative of radius in respect to time is 1/2 dh dt. And our height is our unknown. Okay, well this helps a lot now when I go to the original equation. And so originally I have two unknowns. But now I can replace radius with the relationship that it has with height. So radius is actually 1/2 height, and that's going to be squared times height. So if I simplify that and clean that up a little bit, we get volume equals 1/3 pi, and then we get 1/2 height squared, which is 1/4 height squared times h, and so we end up with 1/12 pi h cubed. There we go. Okay, so now let's take the derivative of that in respect to time. So we're going to get the derivative of volume with respect to time is equal, the constant stays the same, 1/12 pi, and then I would bring the 3 front, 3 h squared dh dt. Okay, so let's substitute the values we know. So we know the change in volume is 2, so we get 2 equals 1/12 pi. Remember, our goal is just to have one variable, times, okay, and then we have 3. Now h is we're concerned when the height is 3, so it would be 3 squared dh dt. Excellent. Now I'm going to solve and write my answer in a sentence. So since I'm having troubles, I'm going to just... So now when I solve for this, I end up, when I reduce it a little bit, I get 2 equals pi over 4 times 3 squared dh dt. And I'm going to leave my answer in pi because that's most exact. So I get 2 equals 9 pi over 4. So I'm going to multiply by the reciprocal. So I end up with 8 over 9 pi dh dt. So what is that? That is the change in the height of the water when the height is 3 meters. So when the height is 3 meters, the height is changing by 8 over 9 pi meters. What is that? Meters per minute? Meters per minute. There we go. Okay, last typical problem. Whoops. Okay, so we have a balloon rising. So let's underline the facts like we usually do. We have a hot air balloon rising up from a level field. Wait, a hot air balloon rising straight up from a level field. So we've got a balloon. As you know, my drawings are not great. It looks more like a tree. It's rising straight up. And it's tracked by a rangefinder 500 feet away. So 500 feet away, I have some guy who's responsible for tracking this balloon. Okay? And we're told, so that's a fact, 500 feet. At the moment, ooh, that's a condition, the rangefinder's elevation angle is pi/4, so we're going to be dealing with angles this time. The angle is increasing at the rate of, so we have a rate, radians per minute. How fast is the balloon rising? So we want to find the change in height over time. So let's fill out our organizer and get this started. So here's my lovely diagram. So the unknown again was what is the rate of change in the height of the balloon with respect to time. Now, what function am I going to use for this? I have an angle and I have a height and then I have the distance 500. Well, I'm going to use some trig because it's an angle. What trig angle uses opposite and adjacent? Well, tangent does. So I am going to be using tangent of theta equals the height over the base, or the distance from where that guy is standing. So what are the things we know? So we've got theta, which is the angle of elevation. So you would write angle of elevation, but I don't have much space in here. Okay, oh, that says elevation. I know you can't read it. So are we given the change in theta over time? I think actually we were, weren't we? Wasn't that 0.14? I'm looking at my notes right now. Yeah, it was 0.14 radians per minute. Okay, now the other variable is h. That's the height of the balloon, and that's what we're actually trying to solve for. So dh dt is my unknown. And now the base, I just call it b for base. Now that's the distance that the guy's standing. Well, he has his scope all set up at 500 feet away. Now that doesn't change. He's not running around. He's staying in put. So the change in the base over time is just going to be 0. So now, since I have a constant, oh wait, condition, there was a condition. I want to know when the angle of elevation is at pi fourths, in other words, 45 degrees, what is the change in the height of the balloon? So now we're going to see if there's any constant to substitute into my equation, and there is. We know the 500, sorry. So we have tangent theta equals 1 over 500 times h. Now let's take the derivative of it with respect to time. So the derivative of tangent is secant squared. So I have secant squared theta, and it's the change in theta over time, is equal to 1 over 500, and it's the change in height over time. Now remember, we only want one variable when we're solving. So do I know theta? Yes, I know that theta is pi fourths. So secant squared of pi fourths. And then I'm going to multiply that by the change in theta, which is 0.14, and that equals 1 over 500 dh dt. So now I got to do a little trig, and let's see, secant of pi fourth, and then we square that. So that would be 2, and, wait, 2? Yes, 2. And then it's times 0.14, and then it's times 500, and that will equal the change in height over time. Okay, so it's 0.28 times 500, so I think I already did the math. It comes out to 140. Now you always write this in a complete sentence. So my sentence would say, when the height of the balloon, when the angle of elevation is pi fourths, the rate of change of the balloon is 140, is it feet per minute? I think so, 140 feet per minute. Okay, now you're going to try a problem. Now I'm going to give you this same scenario with 3 different questions. So the first question is, you are given the length L of a rectangle is decreasing at a rate of 2 centimeters per second. So you're given a decreasing rate. The width is increasing at a rate of 2 centimeters per second. So there's another rate. When, so this is a condition, length is 12 and width is 5 centimeters, find the rate of change of area. So pause the video, you do this by yourself, and then check your answer. Okay, so now let's check your work and see how you did. You can see at this point I've just written down all of the facts. Make sure you have all of your facts known. I forgot to write, though, the unknown. The unknown is we're trying to find the change in area over time. Okay, so it's length, it's area of a rectangle, so that's length times width. So now I'm going to take the derivative. So the derivative of area in respect to time, product rule, length stays the same, derivative of width with respect to time, plus the second term width stays the same, derivative of length with respect to time. Now I substitute all that I know. The derivative of area with respect to time, that's my unknown. The condition says when the length is 12, and we know the dw dt is 2, and then the width is 5, and the change in length over time is negative 2. So when I do that work then, I get 24 minus 10, which is 14. Now 14 what? Remember, it's change in area over time. So it's going to be centimeters squared per second. Did you get the area? Did you get the units right? Okay, now here's another one, similar problem. So notice the situation is exactly the same, but this time I want you to find the rate of change of perimeter. So stop the video and do this one on your own. Okay, let's see how you did. So I have all the facts written down, and we know perimeter of a rectangle is 2 length plus 2 width. So when you take the derivative in respect to time, we have the change in perimeter with respect to time, and it's 2 times the derivative, oops, I kind of started writing that wrong, derivative of length in respect to time, plus 2 times the derivative of width in respect to time. And now we substitute in all the values we know. Now we don't know the change in perimeter over time. That's our unknown. Equals, now it's 2 times the change in length over time, which is 2, negative 2, sorry, and then plus 2 times the change in width over time, which is 2. So I end up with negative 4 plus 4, which is 0. It's kind of weird. What does that mean? Does that mean that the rate of change of perimeter is 0? It's not changing? Good question. Okay, moving right along, last scenario. Okay, so you can see in this problem now, you have to find the rate of change of the length of the diagonal. Stop the video and then check your answer. Okay, so I didn't rewrite everything because we know the facts are still the same. The only thing that changes really is our formula because we want to use Pythagorean Theorem. So now I'm going to take the derivative of the diagonal with respect to time. So I'm going to get 2L derivative of length in respect to time plus 2W derivative of W with respect to time plus equals, 2D, and that's the derivative of the diagonal with respect to time. So now I substitute in all the values that I know. Well, I know the length is at 12, so 2 times 12, and then the change in length is negative 2. And then the width is 5, and the change in width at time is 2. Now, I don't know the length of the diagonal, and I don't know the rate of change. So you can see we have a dilemma here because I have 2 unknowns. Is there any way I can find the length of the diagonal given that I'm looking at it when it's 5 and 12? Well, of course I can. I can do Pythagorean Theorem. So what is 5 squared plus 12 squared will equal the diagonal squared? Well, 25 plus 144 is 169 equals diagonal squared, so we know that the diagonal is 13. So I can replace the length of the diagonal with 13. And my unknown is the change in the diagonal with respect to time. So I do the math here then, and I get negative 48 plus 20, 4 times, equals 26 times the change in the diagonal over time. And I get negative 28 divided by 26, which we know can be reduced to what, negative 14 over 13? Yeah. So this is the change in the diagonal with respect to time. So that means the rate of change of the diagonal is actually decreasing when the length is 12 and when the width is 5. And it would be centimeters per second. Great. Phew, we finished.